Hello, everybody. Welcome back to Computer Science 3200. How's it going? Man, it is getting dark out so quickly. It's like 3:30 and it's already getting dark out. It's crazy. I guess winter is coming. All right. So we have finished our section on reinforcement learning. There's a lot more out there in the world to do with reinforcement learning, but we're not going to cover it because this is sort of a jack of all trades type of intro to AI class. So today, it wouldn't be an AI class if we didn't talk a little bit about neural networks. There is an entire machine learning course at MUN, so if you are interested in deep diving into neural nets, please, by all means, go do that. So the way we're going to cover neural nets in this class, we're going to have a fun few classes coming up. So in this class, I'm going to go over sort of a little bit of history and the base mathematics of neural nets. Then in the next lecture, you're actually going to watch this YouTube video. That new YouTube video is better than I could do. It's pretty much the optimal YouTube video for actually implementing a neural net. And I want you to watch that because it goes over exactly how you would implement a neural net. Then in the next lecture after that, we're going to talk about what deep neural networks are. And after that, you are going to watch a movie. And so the movie is called AlphaGo, and it is about how Google DeepMind created the world's best Go playing program. And the reason we're watching this is not only because it's educational, but because it pretty much incorporates everything that we have done in this class so far, except evolutionary algorithms. So there's search, there's machine learning, there's neural networks, there's reinforcement learning. All of that goes into actually building AlphaGo. So I think it's kind of a nice little cap off to the course to finish with that movie. And despite this being a movie and this being a separate YouTube video, there will be exam questions about both of those things. So you do have to go watch them. All right, so let's hop into neural networks and see what they're all about. All right, so lecture number 18, Intro to Neural Networks. A little bit of a funny anecdote before we get into what neural nets are. In 2010, MIT, the famous school, they were reviewing which topics that they should drop from their AI course in order to make room for more modern techniques. Because believe it or not, there's a lot of techniques that people have used over the years for AI that have not really amounted to much. And so they're sort of there for historical reasons only. And in 2010, MIT was about to cut neural nets out of its course completely. And they decided to leave them in just because they were like, this interesting thing that had been done historically. Maybe they also sort of simulated what the brain did. But in almost 30 years of research, neural networks, now, okay, people are going to argue with this. Yes, there were some interesting results with neural nets, but there were things that were more fashionable and producing better results than neural nets. And so the funny thing here is that neural nets were almost on their way out of the MIT AI course in 2010, as recently as that. But then something happened. Deep neural networks happened. And in 2012, this paper came out, which was by Geoffrey Hinton at the University of Toronto, on image classification with deep neural networks. And the neural network was gigantic. It used a ton of computation. And this ImageNet classification problem had 1,000 categories of images, hundreds of thousands of images, and you had to classify what the image was. And it absolutely blew away the competition. So it turned out that when you take neural networks and you add this thing called convolution and you blow them up to a massive scale and you run them on a ton of parallel hardware, they actually start to do things that are really cool. So deep neural networks in the last few years have been responsible for leaps and bounds in image processing. Here we have AlphaGo that we'll have a whole movie about AlphaGo. This is the Poker Research Group from the University of Alberta. Lots of really great things have happened in the last just few years, in the last decade, from neural nets. So let's talk about neural nets and why they are now back in the MIT course about AI. So neural networks, you know, I love this comic. It's like, okay, some math and then a miracle occurs and then some good results happen. This is basically what a neural net is, right? Turns out that a neural net isn't magic. It's just math. And so there's a bit of math, but we'll go through that math in this lecture. But before we go through the math, let's talk about what the brain does a little bit. The differences between a brain and a computer. So here we have two columns. One is for the brain and one is for a computer. In terms of processing units, a computer has typically a few CPUs, maybe a few billion transistors. The brain instead has 100 times more neurons than a typical computer has transistors. Storage capacity, a computer has, you know, on the order of gigabytes of RAM and let's say terabytes or even petabytes of non-volatile or disk memory. The brain, on the other hand, has a bunch of neurons and a bunch of synapses between those neurons. And so in terms of hardware, the brain has a lot of synapses between its many neurons, okay? However, a computer can do processing at a billionth of a second, but the brain is not processing that fast. In terms of, so what the brain does, essentially, if you want to reduce the brain to a computer, is that it has more hardware that computes slower than a computer, but it is far more parallelized than a computer. And so the bandwidth of what happens in a brain is far, far, far greater than a modern computer. And inside your brain, you have neurons. So this is the I am not a biologist diagram of a biological neuron. And so the reason I'm presenting it like this is because we are going to create an artificial neuron that will be part of a neural network. And it does resemble the actual neuron that's in the brain. So what people believe is that these artificial neurons that create artificial neural networks are mimicking sort of what happens in the brain. It is not exact by any means, but there's an analogy there. So in an actual biological neurons, we have these dendrites. Those are input signals that come from actually other neurons. Then you have something going on in here, which isn't that important. And then we have output signals. So the axons from one neuron extend to the dendrites of another neuron. So we have the axons out here. Those are the outputs. Those are going to be the inputs for other neurons. Stimulation of the dendritic tree of a neuron may cause the axon to spike like a transmission line and actually produce an electric signal. After firing, the neuron will go quiet for a while, and then firing can affect the surrounding and connected neurons and cause a chain reaction. So I'm not going into the biology of this. All I want to show you is this diagram and that there is an analogy in the real human brain between input signals and then some stuff going on, and then output signals, which go to the inputs of other neurons. So before we get into neural nets or even artificial neurons, we start with the beginning. And in the beginning, there were threshold logic units. So what in the hell is a threshold logic unit? Well, this down here is a threshold logic unit, or TLU. It has several parts to it. The first part is some inputs. And so these inputs are going to be x1, x2, x3. So x are the inputs to this system, what you are going to pass into it. And in a TLU, those are binary. So for example, the analogy to the real neuron is, did the thing fire or did it not fire, right? So we have inputs and then we have weights. Those weights are going to be real values, right? So real numbers, typically between 0 and 1, something like that. And then what happens is the inputs are multiplied by the weights. So we have x1 times w1 plus x2 times w2, xn times wn, and all of those are summed. And then the output is a spike if the sum meets this threshold. Okay, so this over here, in terms of mathematics, is what's happened. We have the sum of wi times xi, and if that is greater than the threshold theta, then the output of this TLU is 1. Otherwise, it's 0. That's it. And so if you sum all of the elements, if you sum the multiplication of all the elements of two vectors, that's called a dot product. So here we just compute the dot product, which is x times w. And if that is greater than the threshold, the output is 1. Otherwise, the output is 0. So you look at this and you're like, okay, well, that's neat. What can that do for us? Well, it turns out by choosing different values for that weight vector, w, we can actually have a TLU compute the output of a different function. So let's just look at a couple of examples of logical operators that you can simulate using a TLU. So up on top here, let's try and do AND. So here we have, crap, I gotta move my camera for this. All right. So on top here, we are trying to simulate the conjunction, or the AND of both of these. So you all know, your logical Boolean logic. So x1 and x2 is going to be, well, here we have our truth table. You've all done truth tables before. So we're going to pass in our x1 and our x2, and the output is going to be 1 if they're both true, and 0 if they're not both true. So just watch this. If we take a TLU and we assign the weights of 3 and 2 and a threshold of 4, then here is what our TLU does. We have x1 and x2, and here are the 4 possible values that you can have for x1 and x2. So if they're both 0, then 3x1 plus 2x2 is going to be 0. And so the output here, you say, is that output greater than 4? If it is, the output's a 1, but it's not, so the output is a 0. Next, we go to x1 being 1 and x2 being 0. So 3x1, that's going to be 3, plus 2x2, that's 0. So we have an output of 3, which is not greater than 4. So the output is 0. Next, we have 0 for x1 and 1 for x2. And we have 3x1 plus 2x2, that's going to be 2, which again, not greater than 0, or not greater than 4, so the output is 0. But finally, we have 1x1, so 1 for x1 and 1 for x2, and then 3x1 plus 2x2 is going to be 5. And look at this. 5 is greater than 4, so the output is 1. So if we have this TLU with 3x1 plus 2x2 for the weights, so 3 and 2 for the weights, this actually computes, and 4 for the threshold, then this computes the exact output of AND, which is pretty neat. We can simulate that function. And here is the real key part, and this is actually the key to like all of neural networks. Let me turn my camera on. This is the key to all of neural networks. So pay attention to this part. Turn it back off. Look over here. What does this actually mean? Can we visualize this somehow? Well, it turns out if we plot x1 as the horizontal axis and x2 as the vertical axis, then if you go back to your linear algebra course, 3x1 plus 2x2 defines a line in the plane, right? So look at that. This is the line 3x1 plus 2x2. That's what that line looks like. And all of the points under the line, meaning less than 4. Oh, sorry, you've got to put the 4 in here as well. So this is 3x1 plus 2x2 plus 4. That's the line. So if it's below the line, all of the results are 0. And if it's above the line, all of the results are 1. So what you have done is you've created the function for a line in the plane separating your possible inputs, the output values, into zeros and ones. That's what the TLU is doing. It's drawing a line through a plane that separates the classes of outputs. So this is really a classifier, all right? We're drawing a line through a plane. On one side is one class, on the other side is the other class. And let's look at the implication as well. So in the implication, we have a similar truth table. I'm not going to go through it all, but if we do have 2x1 minus 2x2, all right, this is x2 implies x1, which is something like not x2 or x1. And so if we work out this truth table, these weights happen to produce the exact output for the truth table. So if you do the same thing with the values of x1 and x2 and draw that line of this function, you get this line where everything below it is is 1 and everything above it is 0. And that's what you are doing. These TLUs, geometrically, you are defining a line through a plane that separates two classes of data. Now, we can do this in multiple dimensions as well. All right, so let me turn that camera back on. So here we have a TLU that approximates x1 and not x2 or x1 and x, so these complex functions, right? Sometimes we can figure out weights for those inputs and a threshold such that you actually get a truth table that matches, and so the TLU can approximate that. But here we see that we have 3 inputs. So when we had 2 inputs, that defines a 2-variable equation, which is a line through a plane. And if we have 3, this is actually a plane through a 3-dimensional space. Okay, if we go to 4, then we're defining like hypercubes and stuff. But that's what we're doing. It is a geometric problem at its heart, where we are separating possible values into 2 parts. So, linear separability. What is linear separability? Well, it's exactly what we've been talking about. Can we draw a straight line that separates perfectly 2 things? So we call 2 points in an n-dimensional space linearly separable if they can be separated by an n-1 dimensional hyperplane. One of these sets may contain points on the hyperplane. And so a Boolean function is called linearly separable if the sets of points of 0 and the sets of points of 1 are linearly separable, right? So we look back here, we have a function right here, we can draw that line through it, therefore this is linearly separable. We can draw a line right here that separates the black points from the white points, so this set is linearly separable. However, consider a different function, which is called by implication or equivalence, which is 1 if the 2 inputs are the same and 0 if they're not the same. There is no separation line here. So I cannot pick a line that separates these 2 sets of data such that all of the 1s are on one side and all of the 0s are on the other side. So this function is not linearly separable. All right? And I might ask you on an exam whether or not a specific function is linearly separable. And what you're going to have to do is maybe draw that truth table or draw this diagram or something like that and say, hey, there's no line. So there's no line that separates it, so it's not linearly separable. It turns out that for single functions, Boolean functions, many more functions are not linearly separable than are linearly separable. So for example, if you have 2 possible inputs, and you look at all the different operators on Boolean inputs or Boolean variables, there are 16 possible Boolean functions of 2 inputs, of which 14 of them are linearly separable. So 14 out of 16, that's not bad. But when you go to 3 inputs, well, there's 256, and so I think this is like 2 to the 2 to the 2 or 3 to the 2 to the 2. Anyway, I can't remember the function for figuring out the number of Boolean functions. But once we get quite high, like here there's 10 to the 19. So what's that? Like 1,000,000 times 1,000,000,000,000 or something like that with 6 inputs, but only 100,000 of them are linear separable. So in general, for many inputs, a single TLU cannot compute that function. All right, it cannot linearly separate because no line exists which can classify them from 0s to 1s. So in order to overcome this, you need networks of TLUs. Okay, and a network of TLUs is essentially going to be drawing a bunch of lines through a plane. We'll get to that. So at first there was the TLU. The TLU worked on Boolean inputs with real valued weights. Then we move on to the perceptron. So the perceptron came right after the TLU, and this starts to look like an actual neuron. So what goes on inside the perceptron? Well, we have our inputs again, but those inputs can be real valued this time. They don't have to be just Boolean variables. We also have our real valued weights. And again, we have that function right here, which is the input times the weight, the sum of all of that. So that's the dot product. And we'll talk about this in a second, but we have an activation function that is going to take the place of the TLU. We'll get to that. But here is this diagram of a perceptron. And if we look, it looks kind of similar to the diagram of the biological neuron, right? We have our inputs over here. We have some internal weights. Then we have some function that's being calculated. And then we have an output. And then, so something in here is causing, you know, some weights to be updated and then produce an output. So the two are quite similar looking, at least at this scale. And then if we tie a bunch of those together, these biological neurons, here is what we can get. It's a very simplified model of the brain, right? Where we have a bunch of inputs, x1, x2, up to xn. Then inside here, there are a bunch of neurons doing something. They are connected somehow. And in the end, we get this output. So we're going to call the output vector y. So our y hat just means this is a vector. So the output vector is a function of the input vector, the weight vector, and the threshold vector. Remember, we had the thresholds back here. And this is going to essentially be what a neural network is. It, just like the brain has a collection of neurons, a neural network is a collection of artificial neurons. Okay? So, what I want to show you real quick is this website. Hang on, let me refresh this. Okay, why does that go like that? Here's the website. I just pasted it in the chat, and here it is. So this is the TensorFlow playground, and what I want to show you is this in real time can do neural network calculations, which is great. Actually, did I have this later on or not? One second. Actually, yeah, I don't want to do this yet. I want to continue on with the lecture first. Sorry, I forgot the order in which I was doing stuff. All right, so we go back to the neural net. We link a bunch of these artificial neurons together. We get a neural network that can do more complex processing, and I'll explain a little bit more of that when we go to the demo. You may have heard of the process of training a neural network. So back here, when we looked at a TLU, we came up with these values of the weights, right? 2, -2, 2. Here we had 3, 2, 5. How did we get to those, right? How did we choose those weights to be the proper weighting values? Well, someone sat down and hand constructed this function. But when you get to larger neural networks, that is no longer a thing that you can do. It becomes very difficult to do those weights by hand. So if you've ever heard of training a neural network, what this does is that you are figuring out the weights over time. And so given some input data and some known output data, you're going to adjust the weights until your neural net predicts the actual outputs. So running the inputs through the network gives us a calculated value, right? So we've got some input vector. We've got y, which is our output vector as a function of those things. And so that's what this is. This is called feeding forward. So we give inputs to the neural network, they run through the neural network, and you get an output. And then training a neural network involves the tuning of the weights and the thresholds until the values we get out of the network match our training data. And so what the neural network is, essentially, is a function approximator. So just like a TLU approximated the output of a function, we are using a larger neural network to be a function approximator for some other function. It could be a very complex function. So how does the training process happen? The training process happens. We are going to have a desired function. That desired function, let's call it D, right? So that's the function we are trying to approximate with our neural network. It could be y equals x squared. It could be, is this image of a dog or a cat? And that is going to be calculated by some actual function called g. So if we have a function, like some oracle function that can actually take the inputs and produce the desired output, that is what this function is. We don't have that function though, so we're trying to approximate it. The neural net function produces an output vector from the inputs, weights, and thresholds. So the performance should be a function of the desired output, which is, the actual function output, and the thing that's output by your neural net, your y. So what some people do, there are different ways of doing this. Most of the time, what you do is you compare some sort of distance or error function between the desired vector and the neural net vector. So you take maybe the difference of them, and then you square it, and that's some square distance. And the best possible performance would be at p equals 0, where you have no difference between the output vector of your neural net and the result of the desired vector. And so what you want to do is attempt to minimize this error, right? So essentially, you have a bunch of labeled data, you pass it into your neural net, and your neural net gives you an output, and you say, how close was that output of the neural net to the actual labeled data? And then based on the difference, the error, you are going to update the weights somehow. So what is the magic behind updating the weights? And again, I'm not going really hardcore into the details here, but I do want to explain sort of what's being done at a high level. So let's say you have weights, and I'm graphing my weights here, W1 along the x-axis and W2 along the y-axis. And what this graph sort of shows is these arrows, the length of the arrow is essentially the error between if I pass in these weights, and we can have many weights, but it's just easier to visualize in 2 dimensions. So if I pass in, let's say, this x1 and this x2, then the value I get is like here somewhere. And so what this graph is trying to visualize, or what it's trying to tell you, is that, oh look, there's a big arrow here. And what this arrow is doing is it's pointing in the direction of like where the weights should actually be, because there's a big error here. There's an error here, but there's no error here, because this is the actual W1 and W2 that you're trying to work towards. So what this shows you is some sort of performance contour. Now, I'm showing you this as an illustration. In reality, you do not have access to this performance contour, right? You'll just be computing errors and knowing how far you are from the goal. So at any given time, we currently have 2 weights, or many weights, but in this case, we have 2 weights, and we want to find the action that brings us closer toward the optimal value of those weights. And so what could we do? Maybe there's like a hill climbing algorithm or a search algorithm we could do. That's actually a little bit intractable. So what they do is this thing called gradient descent. Okay, so gradient descent is a class of algorithms where, let's say that my initial weight leads me here. Okay, and where I want to be is down here somewhere. So what they do is they calculate the error, they find the direction of the error, and then they move the weight toward that direction. And eventually, especially if this is a convex problem where there's no local optima, eventually you move the weight in the correct direction toward the actual, the correct value of the weight that you want. So what you see over here is you have some starting point. You compute the error gradient. That's why it's called gradient descent. So maybe you compute, okay, this is the error gradient. We are going to move in this direction and get to this point. Then we compute that gradient and move a little bit in that direction. We get this gradient, we move in that direction, we get it here, until we converge and our errors get less and less and less. This can be done in multiple dimensions. Okay, so if we have multiple weights, we can do that in multiple directions or in multiple dimensions. This is just sort of a visualization of that sort of thing, where this is our x's, our inputs, and the output here is the error function. So we go from places of higher error typically down to places of lower error. And so in order to do this gradient descent, something that's really, really important is that we need to be able to take some partial derivatives. Okay, now I know that this is getting a little bit complicated. You don't need to know all the mathematics behind it. I'm not getting down into the weeds with gradient descent. But the important part is, in order to calculate the error's direction so that you can update the weights properly, and you descend in error and you go towards a better value. And so this only works when you have a differentiable function. However, if we look back to our fundamental unit of a neural network, our neuron, what we have here is this threshold or activation function, where, remember back in the TLU when we had like 3x1 plus 2x2, if that's greater than 4, right? We had that thing. Well, the way that you actually implement if this is greater than this, then do something, is with this sort of stepwise activation function. So for example, if I have my xy, then it might look something like this. My output, my y value is 0, 0, 0, 0, 0, 0, until I hit some point at which my output is 1, right? So that's how an if statement works, essentially. My output is 0, 0, 0. Oh, I reach a certain value. Now my output is 1 from now on. As the value increases, like, you know, we're at 0, 1, 2, 3, 4. Oh, once we hit greater than 4, now our output is 1 instead of 0. So that's what this activation function is. It essentially represents that if statement. And the good thing about this is that it's easy to calculate, but the bad thing is that this is a stepwise function, which is not differentiable. Okay, so that's not differentiable, so we cannot use a simple thresholding unit and then use gradient descent on that, because it's not differentiable. So thresholding makes our function non-differentiable and annoying to compute. So ideally, what we want is for our output vector to be a function of the inputs and the weights and not have to rely on that threshold. And so one of the ways that they've done away with this threshold is by having this thing called a bias neuron. So a bias neuron in the network is an extra neuron added to each layer. I really didn't explain layers, did I? I think I missed an entire slide somewhere, and I sincerely apologize for that. So a neural network is made up of different layers of neurons. You have an input layer, you have some middle hidden layers, and you have an output layer. And essentially, all you're doing is that the output from one layer is the inputs to different layers. Okay, so I apologize for that. I don't know how I could have skipped by that very important step of actually explaining what a neural network is. So in order to remove the threshold, you add an extra neuron to each layer. That neuron has a fixed output value of 1, and it has a similar effect to doing that of the thresholding, but it's easier to compute now. So this is what I mean by that, okay? Let's say we have what we had before with our perceptron, which has a threshold. So if the dot product is greater than a given threshold, our output is 1, otherwise it's 0. Instead of doing it this way, we can do the following. We can get rid of having different thresholds by putting an extra bias neuron here and setting the weight of that bias neuron to negative theta. So down here we have the exact same function, but it's represented in a different way. So here we said, is the dot product greater than or equal to theta? Well, then my output fires. But here, instead, I've just brought that theta over here to the left-hand side, and now I can say, well, is the dot product minus theta greater than or equal to 0? The idea being, when you train your neural net now, it finds the weight here and it finds that threshold for you. So that's the first part, is getting rid of the value of theta here so that our activation function can always be centered around 0. And the second part is to smooth out that activation function so that it becomes differentiable. And so what happens is they apply a sigmoid function to the activation in order to smooth it out. So here you see this is a step function where it is 0, 0, 0, 0. Oh, now it's positive 1 immediately. And so you can also have sine functions which go from negative 1 to positive 1 immediately. And what we do is we apply something called a sigmoid function to that in order to smooth that out. So this is a function which is differentiable at all points. It is not a hard cutoff at any particular spot. And there are many, many different types of sigmoid functions. Here is one example. Here are a bunch of examples. But essentially, when you run a neural net, you're going to have to choose your sigmoid function. They all have slightly different properties. And what it does is it replaces the thresholding part. Okay? So this is the improved neuron. We have our inputs, we have our weights, we have our bias neuron. It has its own weight. Then the network computes the dot product of the inputs and the weights, runs it through this now smooth activation sigmoid function, and we get our output. All right, so we take a bunch of those neurons, and then we have an input layer which passes inputs to our network. We have one or more hidden layers. They're called hidden layers because they're not input or output. And then we have an output layer. And through the process of gradient descent, we will update our weights and ideally produce the correct output. So a common structure of the neural net is that it's fully connected, meaning that all of the inputs, so this is a fully connected network. What fully connected means is that the output of one layer is fed to all of the inputs of the next layer. That just means fully connected. If we start with a fully connected network, then unimportant connections will eventually train to a low weight. And I'll show an example of this. All of this will become much more clear when I actually show the example. And so the network could have an arbitrary structure. However, let me rewind a bit. So typically what we can do is just pass in a fully connected network, and if any of those weights are not important, they will go to 0. But the network can have an arbitrary structure, and some research within the neural net sphere is actually on how we can learn the best structure for a neural network. So what we get is this sort of process. Here we're doing some training. We are passing in pixels of an image as the input to our network. And here's the input to our network. This is a fully connected network. So here we pass in a specific number. Let's say it's an image of 4. And we also pass it in the correct output, which is 4. The outputs of this neural network are the numbers, different outputs from 0 to 9, right? So the input is an image, and then what will happen is we get output values on each of these output nodes, and whichever one is the highest, that is the thing that the neural network thinks it is. So we pass it in, we pass in this image of a 5, we say, okay, we think that's a 3. Then there's a difference vector that's calculated between, okay, you thought it was a 3, but it's actually a 5, and we do gradient descent to backpropagate these weights, update the weights in the network, and hopefully our next guess at a next number is going to be more accurate. So we do this tens of thousands, if not millions of times, and by the end, we actually get our neural network, which is fully trained and can predict things well. Here is a video on neural nets, an implementation of neural nets in C++. It doesn't matter that this is in C++. They use very little actual C++ terminology. All you need to know is classes. and arrays and you know classes and arrays. So please watch this video. It is an excellently explained video on how all of a neural network connects. And now what we are going to do is actually look at a demo of a neural net and tie all of this together and see what the hell is going on. Okay. Now we're going to pull up this demo. And all right. So this is that TensorFlow playground link that's in the slides and also out in the chat. So follow along if you want. Here what we have is input points. So we have training data over here. Let me refresh. So over here, we have some different training sets. We have 1, 2, 3, 4 different training sets. The first training set, we have some X1s and some X2s. So we have the X and Y values of both of those. Okay. And we can see here that we have a classifier, and these points are either classified as blue or as orange. Whatever that means, doesn't really matter. But we have a classifier, and that classifier is either blue or orange. So ideally, what our neural net would be able to do, if run, would be able to take in the value of a new unseen point and predict whether or not that should be orange or that should be blue, right? So if you as a human were asked to do this prediction, you could kind of see, okay, well, it looks like this circle here, well, inside this circle should be blue and outside that circle should be yellow or orange. So that's what the neural net wants to do. And if we click run here, we see that after a few iterations, we actually get a neural net which learns to correctly predict this. So this neural network has a structure. We have inputs, we have 2 hidden layers here, and we have an output. Now, we can change the number of hidden layers, we can change the number of neurons per layer, and you might ask yourself, how the hell do we know what structure the neural net should have? So if I run this again, okay, it learns to predict it properly. But the problem with a neural net is that the more neurons you add, the longer the training takes. So let's try and do an example where we try and come up with the minimal possible structure to predict something like this. So using what we've learned so far, let's go to the blackboard. Okay. So what I showed before essentially showed the following, was that we have, let me do a fill. Okay. I'm going to have some points here in my graph, right? So these points over here are black, and these points over here are white. And what we're trying to do is find the line that separates the black points from the white points, or the ones from the zeros, or the blue from the orange, whatever our data is. Now, if these are linearly separable, then that's pretty easy. But if I go ahead and screenshot this and bring it back over here, look at this. Can I draw a single line that separates these 2 data sets? I don't think so, right? What I've basically got to be able to do here is encircle this data set in order to predict it. So let's go back real quick and let's just show. Using 1 neuron as a predictor, that is 1 line that I get to draw through the space. So if I say, okay, I'm going to have 1 neuron and I click run, what this is now trying to do is it's trying to classify things with 1 line. So it's trying to find the best possible line to separate the blue points from the orange points. And as you know, that is pretty impossible to do, but it's going to try its best. So if we pause this and we now think, okay, how am I actually going to separate this? Well, basically what I've got to be able to do is draw some sort of structure that encapsulates the blue points, but not the orange points. So how many lines do I need to have in a 2-dimensional space in order to enclose something, right? Well, I can't have 2 lines, but maybe I could have 3 lines. So look at this. This is actually a pretty good classifier using 3 lines through this space. So let's go back and we will add 2 neurons. So what this is doing now is it is going to try and find a set of 3 lines that can separate the blue points from the orange points. And just to show you with 2 lines, okay, what would it do with 2 lines? Well, it's kind of learning okay, but you know, anything in between these 2 lines it's saying is blue, which is actually kind of accurate, but it's also getting some oranges in there. So let's put another, a 3rd line in there and see what happens. And you can see that yes, we actually do get this like triangular structure that we predicted, which is able to successfully encapsulate the blue points and separate them from the orange points. So to me, this was kind of a revelation to me in how neural networks actually work, at least in a 2-dimensional space. It gets kind of more difficult as you go to multi-dimensions, but each neuron is essentially taking your data, putting it in whatever dimensional space you have, and then trying to draw that like hyperplane, which in this case is a line, to separate one class from another class. And so that's what it's doing here. And if we go over to this data set, which is a little bit simpler, right? We can go all the way down to 1 neuron because it will be very easy to find a single line that classifies the blue points from the red points or from the orange points. Now, that doesn't mean that we can't have a network like this, right? But this network is very complex. It has a lot of weights. It has a lot of neurons. And so in the end, we might get a proper classifier, but look at this. If there's so many different variables, so many of them end up not really meaning a lot, and it just takes longer to train, right? So why would we have this? Let me see if I can do that in a better way here. So let's try and train this. Okay, it did it pretty fast because it's doing a lot of iterations per second, but trust me when I say that this takes a lot less time in practice to train than the one with a bunch of hidden layers, right? So that's what we're doing here. Now, if I go to this case, we can try and see, okay, how does the neural network do? Well, this is a single line. A single line doesn't classify these very well. Let's go to a second line. All right, it's kind of separating some blues. Let's just jump to 4 lines. See if this will work. Oh, now we're starting to get somewhere. It's starting to separate something. So it's kind of separating them. Let's put in another hidden layer. Let's do 2 and 2 and see how this does. So what's happening here? Instead of just drawing 4 lines, what we now are doing is taking the outputs of these lines and classifying on those. So the output space of the previous layer is now what's trying to be linearly separated by the next layer. So essentially what we're doing here is one layer is finding these patterns, and those are linear patterns with respect to the inputs. And then the next layer is trying to find linear patterns with respect to the previous layer. And so you have patterns on patterns on patterns and patterns. And if you actually look at the output from like deep neural nets, what you'll see is like on the very first layer, there might be some edges detected, like the outline of like the side of a line or something like that. Then in the second layer, we'll have 2 lines which form like maybe the corner of a nose or the corner of an ear. And then the third one, you'll maybe actually see the shape of an ear or the shape of a nose. And by the end, we're classifying faces and stuff. So that's what's happening inside a neural network. However, something else that's important that I want to show you is we're going to go back to this example, and I'll go back to the blackboard. So not only does it matter how many lines that we're drawing, but it also matters the space that we pass the points in, right? So here we have, if you had to describe this data structure to someone, let's say we have our X and Y axis like this. Okay, so this is our X axis. Oh geez, that's small. 1 second. Come on, paint. All right, this is our X axis, this is our Y axis. So if you describe this in terms of XY coordinates, then this is actually a little bit difficult to separate, because you have to say, okay, draw a circle around these in XY, or draw these lines around it, etc. And then inside of that is blue, outside of that is orange. But instead of just, constructing a huge neural net and hoping that it figures that out, could we possibly transform the data before passing it into a neural net? And the answer is yes. So instead of looking at this in terms of X and Y, how about we classify points instead by distance from the origin? So if we say, okay, all of the blue points are within a certain distance of the origin, and all of the orange points are within a different distance to the origin, then what we get is, in the space of distances, these two things are linearly separable, right? Because essentially, I've got a bunch of numbers representing the distance from the origin. So for example, I could say anything below a 3 is blue, anything greater than a 3 is 5. So if I'm just trying to differentiate between greater than 5 or less than 5, I can do that with a single line. So if we go back to this here, what you can actually see is that over here, we can transform the data a little bit before we pass it into the neural network. And one of the things that we can do is, instead of passing in the X and Y values, we can pass in X1 times X2. All right, so if we do this with a single neuron, oh, sorry, that's the wrong one. This is the X distance and the Y distance. If it's the distance from the origin in the X and the distance from the origin in the Y, instead of just the X and the Y values, then here with a single neuron, we can classify this set of points perfectly. Why? It's because in the distance space, it is linearly separable. There's a single line that we can draw between distance to the origin. Okay? And that, I don't know about you, but that's really cool. Is that what we couldn't do with a single neuron before? If we transform the data somehow before we pass it in, we can do it with a single neuron now. So if you ever do go on to use neural nets and you're trying to do training in a specific space, make sure that you, transform your data properly, because your learning will be much, much easier. If, however, we have these inputs for this data set and we try and train, well, this is actually quite difficult now, because these data points, the classification of these data points are in no way, shape, or form correlated to their distance from the origin, right? So if we're using that space, we may have to have, I don't know, can we even do it with a more complicated network? No, we can't. So how you represent your data as well is also very important. All right, so what I would like you to do is play around with this, because I might ask you on the exam, here's a data set. How could you shape your data, or would you reshape your data? How would you pass these points in order to most effectively create a neural network with the least amount of neurons for that, right? So for example, here, I won't ask you anything super complicated, like something like this might be fair game. Something like this spiral, this is kind of a hard one. That's a hard one to solve. So play around with this, please. You can look at these are the activation functions. Those are all the sigmoid functions we talked about. You can adjust the learning rate. You can talk about whether this is classification or regression, et cetera, et cetera. All right, so play around with this, and understand what I have said so far. Get to that point where you're understanding that. All right, just to finish off the lecture, neural networks, the applications of neural networks are vast these days. They have become neural networks have become so popular and so powerful that people think AI is just neural nets, but it's not whatsoever. So neural nets are a method for performing function approximation. Given a number of inputs and a desired output or training data, you can learn the function that computes the correct values. And if your neural net is big enough and you've got enough electricity and GPUs, you can pretty much learn that. So for example, you could learn image classification, right? We talked about that already. We've got some hidden layers, some output neurons. We can learn to classify images. We could learn heuristics. So for example, in our assignment, maybe what we could do is compute all the shortest paths on the map from each point to another point, and then train a neural network to actually compute the heuristic, which is the distance. And then maybe we could use that neural network as the heuristic function for A star, instead of trying to come up with our own heuristic function. What AlphaGo did, which we'll see, we'll learn more about this as time goes on, it actually combined deep learning with heuristic search. And it learned two networks, the value network and a policy network. The value network was sort of like, how much do I want to be in this state? You can think of that as the heuristic function. And the policy function was learned, hey, what sort of moves are good at this state? And so that's what the initial version of AlphaGo did. So what AlphaGo did is it used deep learning, and it took hundreds of thousands of professional human replays, and it learned a policy network where the input was a state, and it tried to learn the move that the human performed. It also learned this value network, which is sort of like a heuristic, which is the input is the state, and the target was who won the game from that state. So how good is it to be the white player? How good is it to be the black player in that state? Then, once it had learned all that it could from humans, it played against itself, and it continued to learn and get stronger and stronger. And as it gets stronger and it plays against itself, it plays against someone who's stronger, and so it just gets stronger and stronger, and that snowballs towards a really good player. And if you take that and you throw in some random moves to do this, like we talked about state exploration in reinforcement learning, then you can learn about states that maybe you didn't visit and get a whole nice sampling of the state space and learn to be a very good player. And so the very last thing that I'll talk about is how that tied all back into heuristic search. So Go has a really large branching factor. Unlike our game of Connect 4, which had 7 moves, Go has 300 plus moves that it can do. When humans look at a Go board, it has a really good abstraction of like what move to perform at a state. Like, oh, don't put your piece in a corner, don't put your piece on the sides. What AlphaGo did was it learned a policy network. And so what it did was, after it watched hundreds of thousands of human games, it could say something like, I think that a human player in this situation, what I've learned is that they might do one of these 3 moves. And so it sort of narrowed down all of these moves to maybe to the 2 or 3 best ones. And so what it did was, at each state where you're doing heuristic search, right? Think of alpha beta. How could you do 300 branching factor alpha beta? That would be gigantic. So what it did was, it took those 300 moves and used the policy network to make it just 3 moves. And so now it can search to depth 20 or 30, where before it could only search to depth 2 or 3. And the search also needed a heuristic function to determine how good a state was, and that's exactly what the value network was. So people looked at the original version of AlphaGo and said, oh, it was all deep learning. But it wasn't. It was a combination of search and deep learning. And so the search part was actually fundamental, but the search was guided by what the neural network had learned, which is narrowing down the branching factor so the problem becomes tractable, and learning a heuristic function. So that was the slightly rushed version of an introduction to neural nets. When it comes to exam questions, let's do that live, shall we? Here we go. So possible exam questions. for neural nets. Compute, explain, and compute the output for a TLU or simple neuron. So for example, I can give you weights and I can give you inputs and you will calculate the output of a TLU. I won't give you any like complex, I'll just say TLU. Describe the structure of a neuron. So that means an artificial neuron, not the biological neuron. Describe the structure of a neural net. Describe, explain, let's put this up here. Explain linear separability and compute whether a simple function is linearly separable. What else? The implementation of neural net / AlphaGo videos could be on the exam. What else could I ask you here? I will not ask any gradient descent questions. That just looks like goddamn questions. All right. Gradient descent. Yeah, I'm not asking anything about gradient descent or backpropagation, and I think that's good enough. So I could ask these on an exam. Cool. All right. So if it's neural nets, we will get into deep neural nets. There'll be a little bit more about deep neural nets in 2 lectures' time, and we'll have different questions that could be asked about deep neural networks. So I think those are separability. I think that's pretty fair for the final exam, is knowing what was in these slides at a basic level. Cool. All right. So really quickly, we go back here. We just did intro to neural nets. I want you to watch the neural net implementation video, which is right here. It is linked on the spreadsheet. So that is an hour long. So you can watch that at double speed if you can understand it. But I want you to know the general principles of implementing a neural network. So sort of the class structure, what types of things go into it, whether or not some things might be parallelizable, etc., etc. Again, I will not ask you the math of any gradient descent on the exam. So that's it. I will see you in a week for the lecture on deep neural networks.